Very great good evening to another gathered here. Once again, I like to welcome all the participants for this Atal sponsors today's online FTP on recent advancements and challenges in integration of IoT and 5G or 6G wireless communication for building the next generation connectivity. And it's my pleasure to welcome our today's resource person, Dr. Gunasekaran Tangavel, Senior Lecturer, ECE, Department of Engineering, University of Technology and Applied Science, Muscat, Oman. Welcome you, sir.
Yes, sir. Thank you. Good evening, all.
Yes. And as part of this, each and every session, there will be a group photography. I request all the participants to turn on your camera, like for the group photography part. Yes. Thank you, all dear participants. You may turn off your camera. Thank you all. Once again, good evening to another gathered here. And before moving to session, I wish to share something about like Dr. Gunasekaran Tangavel sir. It's my pleasure to introduce our speaker, Dr. Gunasekaran Tangavel. He's a senior lecturer, EC, in the Department of Engineering at the University of Technology and Applied Sciences, Muscat, Oman. He completed his Bachelor of Engineering in Electronics and Communication from Bardiyar University in the year of 2000. His Master's in Communication Engineering from Birla Institute of Technology and Science in the year of 2003 and obtained his doctorate from Anna University in the year of 2013. Dr. Gunasekaran Tangavel has more than 24 years of teaching and research experience. He has published more than 50 research papers in reputed journals and conferences in the field of wireless communication, antenna design, and signal processing. He also holds 5 patents with his innovative skills. His research interests includes wireless channel modeling and planning, antenna design for 5G and beyond, and bioelectromagnetism. He is a senior member of IEEE and a professional member in IST. There is no limit for his success. We are very honored to have him with us today. I would call upon Dr. Gunasekaran Tangavel sir to take over the session. Please, sir.
Good evening, all. Am I audible?
Yes, sir, you are audible.
Yes, sir.
Thank you. Is my screen visible now?
Yes, sir, it's visible.
Okay. A very good evening to one and all present here. Dear organizers, faculty members, colleagues, and friends, I'm very happy to be with you in the AICT Teaching Learning FDP. Today's topic is terahertz and millimeter wave communication and smart antenna technologies for 5G networks. For the next 1 hour, 15 minutes, I'm going to deliver the demand for these type of wireless communication systems. What is the need for this terahertz and millimeter wave frequency spectrum. And second, as our research area related with antenna, I will give you light on the antenna technologies for these millimeter wave and terahertz frequencies. As we all know, there is a huge demand for high transmission data rates. Could you imagine what could be the data rate? Can you compare the data rate of the current 4G network, what we are experiencing? When this 4G is deploying, the promised theoretical data rate is 300 megabits per second. After deployment, could we experience that particular speed, download speed? What could be the deviation and why these deviations are happening? So we have to be in a position to bridge the gap between high transmission data rate, low latency, high reliability, and interference-free operation. We know the applications ranging from information communication technology, healthcare, smart city, smart industrial applications, like you can add many things. So the need is driving the development of wireless networks, fostering the exploration of new spectrum. So the new spectrum is the millimeter wave and the terahertz. And you could see the antennas are the integral part of these systems. And selecting a suitable antenna is a critical for the future wireless networks which are operating at this particular frequency range. So with this introduction, I will start the spectrum of the 5G. It has two frequency band. One is called FR1, another one is called FR2. The FR1 is the lower spectrum up to 7.125 gigahertz, which is under operation. So it starts around 700 or 800 megahertz to 7.125 gigahertz. This FR2 is the millimeter wave frequency. So imagine there are certain frequency bands which have been lying between 700 megahertz to 7.125 gigahertz, which we call it as lower band of the 5G. Certainly, why we need FR2, the millimeter wave spectrum? Why can't we use only the millimeter wave spectrum for the 5G? Why we need this lower band? This is the first question. Let us discuss about the limitations of this particular frequency based on the complexity and the data rate which we require. So before going to deal this particular frequency range, imagine the first generation wireless communication system, which is analog. Okay, and there is no value added services. It is like our normal telephone. Instead of wired, the channel will be a wireless channel, isn't it? Now we are moving from 1G to 2G. The analog modulation schemes are replaced with the digital modulation techniques and the communication become digital. Then slowly we have introduced 2G to 3G. And you know, when 2G systems are evolving, complete 1G services are shut down across the globe. At least 70 to 80% of the 1G towers were switched off. Then 2G have been evolved. When 3G is ended, we call it as UMTS, Universal Mobile Telecommunication Services. Still, it is in operation in few countries. Okay, but when this 3G comes, it is not replacing this 2G. 2G is still alive. When 4G has been introduced, almost around 70% of the 3G towers are replaced. Now few countries are using this 3G. They are also going to shut down very soon. But still your 2G is alive. Now we are talking about this 5G in two spectrum. One is FR1 and FR2. It is not going to replace your 4G. It is not going to replace your 2G. Why still we are withstand with this 2G? Why the 2G towers are not replaced? So there are two reasons for this. The establishment cost And the backbone for this particular wireless communication systems, still it is evolving with the 2G for voice calls. Only the data networks in few countries, they are using this 4G and this 5G also. So similarly, as this 5G is going to evolve, it is not going to completely replace this 4G system. So then why we need this 5G? First of all, let us discuss about the free space path loss. This is one of the major parameter which directly proportional to the frequency and the distance, the coverage. Whenever we say frequency, as a telecom engineers, we know frequency means it is nothing but your bandwidth, operating bandwidth, which decides the operating bandwidth frequency. The next one is the coverage area, the distance between the transmitter and the receiver. So imagine the simple basic propagation loss, that is path loss model, free space path loss model, we call it as. So the parameter which affects this path loss without taking logarithmic scale, path loss is equal to, so simply we can say 4 pi r by lambda the whole square. So I just replace this lambda by c over f. So the formula will be 4 pi r by c into f the whole square. Now, just compare your 2G spectrum. The lower band of 2G spectrum is 800 megahertz. Okay. Then your 4G, the current LTE system is 2.4 gigahertz. Now your 5G FR1. So as I said, it maximum it can go up to 7.125 giga. Your FR2 will go millimeter wave. For example, the sub-millimeter wave of 18 gigahertz, it may go up to 300 gigahertz. So far, the device availability is up to 56, 24 gigahertz signals. So we could consider the maximum, for example, 24 or 26 gigahertz or 28 gigahertz. Substitute this F over here for 800 mega, 2.4 giga, 7.125 and 24 or 28. So the path loss is keep on increasing when you increase the frequency. So that I have shown here in this diagram, this is FR1, the lower spectrum. Look at the coverage. And it can also penetrate these buildings. The high rise structures are not affecting the electromagnetic propagation. It passes through the buildings. Look at this millimeter wave spectrum. These waves are not passing through this particular buildings. So the coverage area becomes very less in comparison with the FR1 or 4G systems. So this is the one of the compromising factor we have to consider. If we want super fast data, we are choosing this high frequency signals, millimeter wave and terahertz, which signals are prone to a very high path loss. So the attenuation parameters are directly proportional to the coverage and the frequency band. So we have to compromise any one of the parameter. Either you want a high speed data rate or you want coverage. So if you want coverage, choose FR1. If you want higher data rate, go to FR2. This is the yardstick we have to follow to remove the bottleneck between these two parameters. So under extreme interference conditions, the complexity of designing communication subsystems like antenna systems or equalizer systems or baseband controlling units, we need novel ideas and innovative solutions to bridge the gap between 4G, 5G, millimeter wave, terahertz frequency ranges. So this was the aim of today's talk. Before going to the problem statement, this is the internal, the one which I am showing here is the internal architecture of a smartphone released in the year 2022. Look at this. This particular mobile phone has LTE MIMO antenna for horizontal polarization, LTE MIMO antenna for vertical polarization, GPS antenna, Wi-Fi antenna, then Bluetooth antenna, PCS CDMA antenna. So it has several set of antennas put together inside a compact device. So when the frequency of operation is keep on increasing, the example like a millimeter wave, your 28 or terahertz 0.1 or 10 terahertz frequencies, those frequencies are considered for future wireless networks by ITUT. So the miniaturization of your antennas and other RF circuits will create an additional complexity for the design process. So we need an approach developing an efficient, cost-effective, scalable antenna solutions for this future wireless communication systems. I hope you all remember this particular word SAR, which is closely related with the regulations given by TROI. TROI is nothing but Telecommunication Regulatory Authority of India. We cannot simply increase the frequency, or we cannot able to increase the transmission power. Okay, so these two are the major resources. One is bandwidth, another one is power. So all telecom engineers, we know the bandwidth and power are the two major resources. Why we are paying money to the service providers? We are using their bandwidth and power. So to cover large geographical area, we may increase the transmission power. So the service providers, the towers, make capable of connecting 3 antennas, 6 sector antennas, 12 sector antennas, like that. But the TROI has a limitation for increasing this power. So that we call it as the regulatory limitations. For every country has its own standard. For your mobile phone, this TROI has given the SAR, the specific absorption rate is 1.6 watts per kilogram for your mobile phone. There are two SAR. When you are keeping your mobile phone near your head, what is the SAR? Then what is the SAR in the body? You can type your mobile model in Google and you can get the SAR. So most of the mobile manufacturers and the researchers, they have to keep the country's regulatory limit to maintain this SCR. This is one of the example I'm showing you what complexity and scalability is approaching towards this novel antenna design at millimeter wave and terahertz frequencies. So as we know, the bandwidth already increased. For example, your LTE 4G system, LTE advanced, each channel has a bandwidth of say 20 megahertz. And your lower band of your 5G system, which is FR1, has a bandwidth of around 100 megahertz. So it is 5 times greater than the 4G system. That's why in India, they are using this 4G towers and they are implementing this 5G antennas within the 4G tower itself. Then they are adding some additional signal processing units and the system becomes a highly interworking between these two frequency band. So the first one we call it as non-standalone mode operation of this 5G. The second one is the standalone mode operation of the 5G. So the non-standalone mode is nothing but the frequency spectrum which is combining at least 4 to 5 LTE channels to put together to form one 5G mobile network bandwidth. That is non-standalone mode. So your 5G is operating in collaboration with the 4G. The standalone mode operation, it is completely using its own carrier frequency for communications. For effective communication, the transmitter side, that is the base station side or your access point side, there is no problem in the space. So you can implement whatever antennas you want to put inside the base station or the access points. Imagine the user equipment, the gadgets what we are using, where the space is limited. We cannot able to integrate these miniaturized antennas put together inside the device. For example, I have shown a chip antenna. When we are using a back cover, you know the plastic cover we are using along with our mobile phone for protecting our phone for any falling or other water resistant matter. So the first one without the back cover, the second diagram indicates the mobile phone with the back cover. You could see addition of this plastic cover, okay, this mobile is having a 4 element chip antenna, okay. So 4 element, 4x4. So it's simply like a MIMO system, okay. So see the radiation pattern, the uniformity maintained in the radiation without the back cover. So look at the radiation pattern here. So the power is scattered around this, so that it will be reducing the efficiency of the received signal. So this will affect the SCR. So even though the mobile manufacturers fixing this SCR in the worst case conditions, so these factors under extreme interference, the complexity of controlling this SCR becomes very tedious. So we need a special type of antennas for this particular frequencies, especially for the user equipment, may help us to resolve this particular problem, like using FSS, that is frequency selective surfaces. Now we are having in the even in the base stations like IRS, intelligent reflection surfaces. So these type of antennas with the metal housing can capable of providing a very good solution for this type of applications. So when enabling the suitable applications like vehicular communication, autonomous systems, or your Internet of Things, smart city, or your extended mobile broadband applications, the mission-to-mission communication types, where the base station terminal antennas and the user equipment terminal antennas have to correlate with its specification and characteristics parameters with respect to the given conditional or environmental conditions. So let us talk about beamforming after 10 minutes. We'll come to this dual connectivity. The RF interference challenges, as I already mentioned, this 5G is in non-standalone mode with LTE. This is problem in the mobile handsets. So your mobile operators can easily switch between standalone to non-standalone. Your device has to switch between these two. That's why I have shown this particular architecture of this mobile. Look at this. So when the operator is using this phone in particular frequency ranges, so you can select either antenna 1 or antenna 2. If it is, for example, 4G communication system, the mobile will switch to this frequency. If it is in the FR1, the mobile will switch into this particular frequency. So the dual connectivity creates a lot of interference inside the handsets. So the dual connectivity, especially with the power amplifiers, they are using only one power amplifier for these two frequency bands. So where this power amplifiers decides the Troy regulatory limitations. So this SCR is specifically controlled by this power amplifiers. We know most of the power amplifiers are non-linear devices, like your CMOS or your JFET devices. So those devices are used for creating or designing this RF applications at the high frequency, or sometimes this heterojunction bipolar transistors. Okay, that is one of the devices, or sometimes this nano electronics may help us to design this power amplifier. So these power amplifiers have to be operated within the limited spectrum given in the band. So if you draw the characteristics of power output and the power input in dBm, okay, the power is measured in dBm. So the expected methodology within the non-linear region like this, if you increase the input power, output power has to increase. But your devices, after a certain stage, it will go to the non-linear region. So there is a huge deviation between the linear and non-linear. You know, the gap between this deviation, linear to non-linear, allowable range is only 1 dB. We call it as 1 dB compression point in the RF amplifiers. So we have to operate this device within this 1 dB compression point. That is a very huge challenge for antenna designers, since the next immediate unit for the antenna is the power amplifier, either at the transmitter end. So close to this antenna, it is a power amplifier, the transmitter. In the receiver also, immediately after the antenna, next one is the RF power amplifier. So the 1 dB compression point measurements will yield to the additional challenges for the antenna designers to match the impedances, especially for the healthcare applications like your pacemakers or other defibrillators. So those things have to be controlled with this particular problems. So these are all some of the use cases for the proposed use cases for the 6G communication system: collaborative robots, e-health, precision healthcare, smart agriculture. Like you can go many applications. If time permits, just go through this universal robots, where this Aerolab has created um, a video for how they are using this particular collaborative robots for enhancing the productivity of their ocular lens in Madurai. Now, let us move to the second part of this particular presentation. As I already told you, this millimeter wave and terahertz spectrum results a huge path loss due to the increase in frequency spectrum. So what are the channel models are needed for this millimeter wave and terahertz wireless systems? So the common channel models usually require to predict the link performance, that is in digital communication modes we call it as bit error rate in a single user scenario. And this particular system is used to predict the performance like the throughput and latency. As we know, the theoretical latency for this 5G system is 1 millisecond. In the meantime, the theoretical latency proposed is 50 millisecond, 40 to 50 millisecond for 4G. But your 5G promises to provide a latency, that is the response time is within 1 millisecond. So we have to verify these things practically. Is it really this 5G systems provide 1 millisecond latency between end-to-end applications? And is it varies? The conditions are varying with respect to huge interfering with the multi-user scenarios. And also we have to check the channel measurements. Really, we have equipment to measure 24 gigahertz, 28 gigahertz signals, and the systems which we have made at this particular points. For example, you choose your network vector network analyzer, simple network vector network analyzer. The available ranges are up to 5 gigahertz in the academic institutions. Like DRDO or other government agencies, they may have a huge amount of spectrum with 50 or 60 gigahertz. This 5 gigahertz spectrum itself provides a costly channel measurement products. So we have to be in a position to correlate these designs with a strong simulation environment before going to the measurements. So there are commonly used channel models. The path loss channel model, as I told you, that is free space path loss. So the path loss factor has been mentioned over there. The second channel model is purely stochastic channel model. Now there are a lot of data sets available based on the measurements given by 4G and 3G systems. So this 5G systems can be trained using your artificial intelligence, either using machine learning or deep learning will help us to create a huge data set, and we can able to model these particular channels. The second one is a spatial channel model. The last one is ray tracing model. So these are all the commonly used channel models for any communication systems. Now we have to choose which model is best for this millimeter wave and terahertz signals. And what are the requirements for this particular channel models? Usually we use the MATLAB toolboxes like communication toolbox, 5G toolbox. For applications, we choose WLAN and LTE. And the antenna toolbox, what we have chosen for our analysis is phased array system toolbox. So these particular toolboxes provide numerous channel models for both generic and standard based applications. You can choose the application like LTE, or you can choose 5G, or you can choose WLAN. Based upon the applications you have chosen, you have to change the channel models. So there are huge amount of document available with this mathworks.com. I have given the link also, you can go through. And this is the progression of channel models starting from the fixed link to mobile user. This is the power or path loss channel model for fixed wireless communication. For mobile user, we are using either time or Doppler shift channel models. Then in wideband communications, we are using a delay spread channel models. Now we are in the era of MIMO, multiple input, multiple output models, where we are using spatial or angular or polarimetric channel models. One of the simplest channel models is Kronecker channel model. But the problem with this Kronecker channel model is it assumes the effective cross correlation in an isotropic manner. So each transmitting antenna and receiving antenna is assumed taken into independent consideration. So in relation with IID, okay, this particular channel model is somewhat simplest method for beginners to test the channels at this particular frequencies. And especially when this 5G millimeter wave spectrum, we are allowing dual mobility. Dual mobility in the sense you are allowing both transmitter and the receiver to move. Your base station is also like conditionally moved in a particular time domain or in the given delay sprint. And also you are giving a massive arrays. So it is not like 2 cross 2 MIMO, or it is not like 4 cross 4 MIMO. It is like something like 32 cross 32, 64 cross 64. Imagine the number of antenna elements over here. Then how the channel models to be predicted with the stationary interferers and mobile interferers. So we need lot of assumptions under this category. So here we are using both non-stationary and stationary models with the spatial consistency, and every model has its own eigenvalue. So we are calculating the eigenvalue spectrum between these two models, and let us evaluate few channels with the frequencies around 18 gigahertz, 24 gigahertz, and zero point 0.1 terahertz. The new requirements for the 5G or 6G channel models, the first one, as we know, this wide frequency range. So where this particular frequency ranges, if we choose the existing frequency models, the channel models like your 2G or 3G channel models, and you simply change the frequency, what will be the result? Let us see. Already existing like your Hata model or other Nagakami or Raisi and Rayleigh, you can choose and you can evaluate up to what frequency ranges these channels provide a significant improvement in the measurement as well as in the channel state information before sending out the channel models. The next one is the broad bandwidth. As I already told you, the minimum bandwidth requirement is 100 megahertz, but it can go up to 500 megahertz, and higher end of this 5G spectrum and terahertz frequencies, the bandwidth may go up to 4 gigahertz. Really, a subscriber needs this particular bandwidth? No. So this will be used for cloud operations like your smart cities or smart agriculture, smart industries like massive mesh type communications. You can collectively take the data from all the CCTV cameras and it will be put up in the cloud. Then you want to access. So those time we need a huge bandwidth to support the reliable and sensitive applications in the society. So these are all some of the scenarios which we have to consider, and conventional 2D channel models are not sufficient. So we need double directional 3-dimensional modeling. So that is another requirement. The next one is smooth time evolution, a spatial consistency. Whenever we speak about the spatial consistency, say this is transmitter 1, this is transmitter 2, this is receiver 1, this is receiver 2 for a 2 cross 2 MIMO. Okay, look at this, the space between these two antennas, the spatial consistency. So antennas are usually a reciprocal device. It may transmit, also it will receive. Imagine antenna 1 transmits, antenna 2 receives, or antenna 2 transmits, antenna 1 receives. So we need a minimum amount of spacing between these two transmitters or receivers. So the consistency, the spatial consistency between these two will yield on the same or similar channel characteristics. You know, if the diversity implies that if one channel goes deep fade, the other channel will not, the closely located channel will not fade. This is the concept of diversity. But here, this concept may not helpful for implementing these type of systems in terms of high frequency and consistency with the other channel model parameters. The next one is massive MIMO. As I already told you, there are number of wavefronts which will be created by each antenna array. So these models should be specifically consistency with the non-stationary modes as well as the channel characteristics to be predicted, unlike the conventional match the filter designs. So we need a new technology to match the symbols transmitted by this particular thing, and the estimation also based on new criterions or new signal processing algorithms, not like your matched filters. So these are all some of the requirements for the channel models based on the applications. The next one is high mobility. For example, if you want to provide Wi-Fi access in the metro trains, the speed of the metro train is maximum of 500 km per hour. So imagine how many access points you want to provide a continuous or seamless wireless connections between end users. So how the channel will behave? Is it maintain a homogeneous, consistent channel? No. Based on number of scatterers inside the train, as well as the movement of the train may create additional reflecting and diffracting parameters in the real world premises. So care must be taken to provide a channel, sufficient channel sound information for this high speed applications, especially the high attitude platform applications like flight. Now we are giving the service providers are giving in-flight Wi-Fi. The flight is also moving with the speed of around 600 to 800 kilometers per hour. Imagine how the channels sound information between the transmitters and the receivers with the localized parameters. So these are all some of the challenging tasks when it is deployed with the applications, and it is the channels must be application specific towards the conditions given in the literatures. There are certain literature is giving the advancements in the massive MIMO channel measurement, and you could see I'm giving only the channel characteristics. Okay, so the first one is the spatial correlation based on K factor. The second method, okay, this has been introduced with a carrier frequency of 5.6 gigahertz. Okay, so here they are using RMS delay spread. Then is there any channel models which is given more than 20, 25, 26 in the outdoor environment? You could see only few channel models are available. So in the outdoor communication, and look at the antenna what they have been used so far for measuring this channel. It is uniform linear array of 12 cross 4. It's a planar array. And the characteristics parameters they consider is only throughput and the effectiveness. That is the reflection characteristics. What of this path loss? What of the acknowledgement packets transmitted over there? What is the latency? So lot of parameters have not been considered so far to introduce the applications or use cases at this particular millimeter wave and terahertz range frequencies. So care must be taken to choose these channel models before designing your antenna. Now look at this particular propagation channel model, which is wide sense stationary uncorrelated scattering. This is the basic channel model for MIMO systems, which will be providing a 3D space-time frequency model. So you can choose any one of this particular model based on your application, and you can start to create your channel state information. Either you can go with this impulse response model, space-time variant, or you can go with the transfer function model with the space-time variant. And either we can work with the time domain or we can work with the frequency domain, since this MATLAB nowadays allowing us, or even your Python, you can write your own code. You can model your channels in time domain or frequency domain based on the characterization parameters which you are choosing towards the system. So these things are based on the Fourier transformation. Simple Fourier transformation will help us to convert the variants from impulse responses to the time domain applications for the given system. This is one of the simulation setup, and how the simulation setup has been done for the channel model, and how many interferers you are collecting, how many moving interferers. For example, in this case, the car is the high speed interfere, mobile interfere, and there are fixed location mobiles. These are all some of the locations which creates a huge amount of interference with the others. So first of all, we have to create antenna array inventory. So here in the test bed, it is already available uniform rectangular array, and assign the base station and mobile locations. Then choose antenna array for the base station and the mobile station. Then you start analyze you want LOS or non-LOS for each link. Then what are the system parameters you can study? Center frequency, power delay profile, angle of arrival, angle of arrival direction, path loss models, number of time samples. And still you can use whatever may be the analysis you want to make with your system. So this is simple setup which help us to model the channel, and you can choose the frequency as well as the bandwidth along with the type of antenna which you want to do. So it is very easy with this 5G MATLAB toolbar to study this MATLAB environment, and there are certain AI channel models are incorporated with this particular 5G toolbox, where this could help us to interface the external data set with your models, and you can able to give you can able to predict the required range of operations and what are the design parameters you have to modify accordingly. We can provide a channel state information to the system. So this is one of the basic path loss channel model output. This RF signal attenuation due to the atmospheric gases. Okay, so look at this atmospheric gas variation at 3 gigahertz LTE. So our LTE is operating at 2.4 gigahertz. So we are allowing the signal to move at to 3 gigahertz. Look at this 2.4 gigahertz. You could find there is a specific attenuation which can be predictable, deterministic. It is not random. So you can able to calculate the attenuation of this particular frequency. And the same time, you could see at 18 gigahertz. Okay, look at the specific attenuation. Look at this value. It is a similar graph sheet. Sorry. So here it is 10 power minus 3, and it is 7.2 or almost 6.6, or you can say worst case it is 7.2. Here look at this, what is the value? It is 10 power minus 1, and this particular problem we cannot able to modulate, or you cannot able to withstand with this particular atmospheric gases, and your signal will be strongly attenuated, and there is no remedial measures to get back these signals. Only solution is retransmission, where you have to sacrifice huge amount of power and the bandwidth. The next one is the RF signal attenuation due to the atmospheric gases at 28 gigahertz and 38 gigahertz. Could you see the comparison here? See, this is at 18, this is at 3, and this is at 18. Look at this graph. This is at 28 and 38. There is a peak attenuation at this particular values. So the signal will be strongly interfering and attenuated at this particular thing. So we need to study these type of channel models by increasing frequencies at terahertz. Here it is only 60 gigahertz, and here it is the terahertz ranges. Look at the variations. So we need a strong probabilistic models to analyze these particular channels. We choose only a basic path loss model. So we can use either a Rayleigh delay spread or a Raytheon or Nagagami or outdoor models or indoor models. You can use the same specific parameters the way how we proceed with this path loss scenario. And this is the path loss channel model for during rainy season. So for example, 20 millimeter per hour rain for 4G LTE. Look at the attenuation characteristics and look at this. And the value will become, here it is 12. And the parameters which are all modifying these values will specifically create the channel state information that is dynamically varying. So we need a dynamic updation every time with respect to the delay spread and the other antenna and channel characteristics. So let us stop this discussion with this path loss model when we move to purely stochastic channels. So we consider this particular stochastic channels with the multipath fading environment. And we are assuming there are phase shifted versions of the signals are incoming, and these signals are processed with the time domain, and the delay spread of the channel is assumed with the first and last multipath component. Okay, and each component has significant energy. These are all some of the assumptions for the purely stochastic channel model. So these are all some of the stochastic channel model examples available in the MATLAB. The basic channel model is AWGN. The next is multipath channel model, WLAN channel model, LTE. The next is 5G, 6G, TDL channel model. So let us take this LTE propagation channel model. The antenna which is used for this example to model this is 2x2 MIMO. So now we have to create the 2x2 4-channel matrix. So each channel matrix, we have to consider the number of transmit antennas and what is the type of input sample you have been chosen, and what is the sampling rate you have been chosen to separate each sample. Here we are using 300 samples per second to correlate the maximum amount of data rate. And the series of impulses allows the changing impulse response of the channel over time. So at 2.4 gigahertz, with each impulse sample spacing between time domain, and the corresponding response is taken for a 2x2 MIMO with the LTE path. You can see the channel impulse response fading for received and first receive antenna and the second receive antenna. You could see how many parallel paths of signal you are getting. So the number of impulses and the spacing between antenna element 1 and antenna element 2, since this antenna element 2 is getting information from antenna element 1, provide a strong correlation between these two, which affects the channel matrix written in the basic models. So we have to create a channel state response when 1 is ideal, 2 is transmitting, and 2 is ideal and 1 is transmitting, like different scenarios. And we could model this one by changing the antenna panel, polarization, and element pattern. Based on that, you can able to create a CDL channel model. So this is the one of the 5G channel measurement model. You could see that they have been measuring this with a different time interval in the order of milliseconds. And this is the channel magnitude, which gives the path gain with the simple output sample of 2 per second. And the another one is the path gain with 2 per second. So we are not calculating the exact bitrate over here. We are measuring only the channel sound information for this. So now slowly this AI channel models are used to predict these channel state information with respect to, for example, if you want to correlate the number of predictions, you can choose the deep learning models and you can train your data set with the available data sets in the publicly available channel data sets. But here the problem is we have to give, we are giving like a balanced data set. If you give imbalanced data set, we know the AI will always predict a wrong prediction and it is very difficult to correlate those things. So when the irregularities of the wireless channels are chosen into consideration, this complex methodologies will help us to achieve an accurate channel model. So we have to create a suitable data set with respect to the existing channel state information and the predicted channel information. Then we can able to correlate these two channel states with the basic considerations. Either you are considering isotropic, or you are considering effective cross correlation, or you are considering scattering parameter model. So which are all the parameters which you are considering will be taken into account. Am I audible? Are you with me? Hello?
Yes, sir.
Yes? Yes. Shall I continue? Since I want to
Yes, sir.
check at least. Okay. Thank you. So now, slowly we will enter into the basic parts of this discussion. What determines the capacity of the network? So far, we are simply telling MIMO and why this MIMO has been chosen for this millimeter wave or terahertz wireless communication systems, and how it is providing theoretically 1,000 times greater capacity than the existing wireless networks. Let us look into this particular formula, which determines the capacity of any wireless network by Shannon's channel information capacity. So the capacity is directly proportional to bandwidth and logarithmically proportional to the given SNR. We know the significance of this logarithmic scale. Logarithmic scale was always compression scales. We know that. For example, basically speaking, if you take logarithmic of base 10 between 10 and 1 lakh, so 10 power 5 I'll write here. So this will become 1 and this will become 5. So between 10 to 1 lakh, the minimum value is 10, maximum value is 1 lakh. The logarithmic scale compresses it into 1 and 5. Why Shannon took this logarithmic scale? He implies that due to the channel state information, the wireless channels, even though you keep on increase the signal power, your capacity will not increase. That was his statement here. So in the information theory, even use either carrier aggregation or any other suitable technologies for beamforming to maintain a certain amount of power to be contaminated through the given user or desired user rather than the interferers. So this logarithmic scale always limits the capacity. That's why the logarithmic scale has been chosen. But this MIMO removes this logarithmic scale or changes this logarithmic scale into linear scale. That is the main advantage of our basic principle of this MIMO. So I have given the base paper for this particular information capacity. Arogyaswamy Palraj is an IITian and he is working in Stanford University. In 2004, he has given an excellent paper regarding this particular deterministic logarithmic scale, and he changed this logarithmic scale into linear scale. Simply, if you go through the paper, you could understand if you use a 2 cross 2 antenna, your capacity is increasing 4 times for the given bandwidth. If you use 4 cross 4, your capacity is increasing 16 times. That's why the future wireless networks are concentrating on high capacity through this mobile model. So our aim is to convert this logarithmic scale into linear scale. It is not so easy when the channel is random. If the channel is deterministic, it is very easy to convert this logarithmic scale into linear scale. But if the channel is, assuming the channel is deterministic, MIMO channel, you could calculate the covariance matrix and you can calculate the mutual information between the transmitter and the receiver for the given frequency. So based upon that, Arogyaswamy Palraj calculated the encoding capacity for the multiple input single output channel, MISO channel. That was his first work. And he proved that for the given SNR, the capacity linearly increases, the encoding capacity linearly increases when you increase the number of transmit and receive antennas. That's why this MIMO capacity has grown into are gaining attention towards the researchers to develop their own antenna parameters with the given channel state informations. So the same work we considered and we took into different conditions in the channel, and we proved that the power azimuth spectrum taken into consideration for the power delay profile and Doppler power spectrum, only these two variants we have considered, along with slow fading, that is shadow fading variations, and excess delays. Only we consider these 4 parameters with the channel model, and we changed different antenna configurations. For example, a planar, uniform linear, circular, concentric circular, and we found that there will be a greater variations in the channel state informations when you change the antenna configurations at the transmitter and the receiver side. So there are 2 categories of MIMO. One is spatial diversity, another one is the spatial multiplexing. So let us take a simple MIMO channel modeling with the stochastic model, that is Kronecker model. Okay. So the assumption for this Kronecker model, if we have to use this S parameter approximation, okay, this S parameter approximation is not very acceptable in the real environment. Why? These S parameters are based on isotropic assumption, as I already mentioned that. So the best way to calculate the effective cross correlation is by using antenna far field parameter. So we have to considering these two techniques for reducing the effective cross correlation and to increase the capacity. We should know what is the value of the effective cross correlation between the transmit and receive co-located antennas. So there are two techniques. One is employing diversity technique. Another one is changing the antenna configuration. So let us take the second category, changing the antenna configuration. Before that, we will develop the model, the Kronecker model, which is the basic channel model, which we consider here. And we have calculated the evaluation of this MIMO capacity with the different spatial correlation matrices. Okay. So while evaluating the spatial correlation, the key parameter which affects the capacity of the system is the parameters, the distance between transmit and receive antennas, and the SNR. And the power delay profile is already considered as a constant value in the transmit and receive models. So the channel parameters are assumed with the Kronecker. Now let us calculate the mean power using field parameters. As I already told you, we are not using S parameter method. So these S parameter models are isotropic models, as we already told you. So we have to go with the far field parameters. So the far field parameters are the electric field coefficient and the sorry, shall I continue?
Yes, sir. You can continue, sir.
Yes, there are two different power delay profile for the mean power. One is the calculation of the effective power through the normalized electric far field pattern, or you can consider the magnetic far field pattern. The simple analysis, we know that E by H is equal to eta in the free space environment. So we have taken the uniform, the three power delay profile here. One is, I will show you that the three models: uniform distribution, Gaussian distribution, and Laplacian distribution for the received waves. For each wave, we are calculating the scenario which is working with the Kronecker model, and we are calculating the mean power. And we are allowing both transmitter and receiver are fixed model. That is first condition. The second condition, transmitter is fixed and the receiver and the interferers are moving. And the third model, both the transmitter and receivers are allowed to move with a certain speed. Okay. Then we are calculating the power delay profile and the spectral parameters based on this electric field and magnetic field parameters. So now we will calculate the normalized radiation pattern. If we evaluate these spatial correlations for the given mean power for simple microstrip antenna, okay, we consider 2x2 MIMO. So each side we are using a simple microstrip antenna to calculate the spatial correlation parameter. So we have to solve the spatial correlation parameter. For example, if I have 2x2 model, I have four equations, that is 4 matrices value. The first one transmit, first one receive, first one transmit, second one receive, then the second one transmits, first one receive, then second one transmits, second one receive. So we need this 4 spatial correlation matrices. So we have to evaluate the 4 parameters in terms of the real power and the imaginary power. As we know, antenna engineers, real power is the real part of the power is the required power, average power, and the imaginary power is the storage. That is, either the energy will be stored in the form of electric, that is electric field or magnetic field, like a capacitive effect or inductive effect. So we have to effectively calculate the spatial correlation for the both real and imaginary parameters. Then once you calculate these parameters, put into loop and come to the simulation setup. Now you choose the joint spatial power spectrum with respect to the azimuth and the elevation parameter. Assume different angles for the azimuth and elevation. Then you plot both the characteristics planes with the spatial correlation matrix. So in this work we consider 2 models. One is spatial correlation for microstrip array, then spatial correlation for dipole array. And let us compare these 2 simple models with the mean arrival angle of around 45 degree in the azimuth plane. Why we have chosen 45 degree? Most of your cellular communications, your phone has to be kept into 90 to 45. That is the first plane. So either you will keep your phone straight with a 90 degree or slightly at 60 degree or 45 degree. So we consider this effect and we started to evaluate the capacity of the mobile network using the same Shannon's information channel theory, then evaluate the eigenvalue spectrum for the given electric field parameter. We assumed these models are considered for chronoker channels, and we are assuming each model is or each antenna is independently acting. That is the only disadvantage of our work. So we are not considering the correlation of 1 and 2 together, 1 and 2 coupled. So we assume 1 independently, 2 independently, and at the same time receiver side 1 independent and 2 independent. So we have 4 correlation matrices. Without correlation, you could see the eigenvalue. There is a huge gap between 1, 2, 3 and 4. And you could see here, when we consider the correlation, when you increase the distribution of the effective spatial correlation power with 0.1 lambda to 2 lambda or 3 lambda, you could see 1 and 2 is strongly correlating with respect to the channel parameter. So we have to estimate this power. What is the amount of power these two antennas are strongly correlating? Due to the strong correlation, the capacity of the wireless network monotonously decreases, and the channel state informations are continuously varying. We cannot able to predict the correct result. So now let us see the spatial correlation versus antenna spacing. So here the antenna spacing in lambda, the spatial correlation is given here with ergodic capacity design, with the azimuth 10 degree, elevation 10 degree, azimuth 60, elevation 60. Our considerations are only the third one, azimuth 45 degree and elevation 10 degree. You could see the spatial correlation matrix is decreasing at 1 lambda distance. So element 1 and element 2 in the MIMO has to be maintained at least 1 lambda distance. Imagine your millimeter wave spectrum, for example, 20 gigahertz for easy calculation of your lambda. Calculate this lambda for this particular case. Lambda is equal to, we know, C over F. Calculate 3 into 10 power 8 divided by 20 into 10 power 9. How small this is. So what could be the spacing between these two? So when you closely place these two transmit and receive antennas, you could able to get a huge correlation among the antenna elements. So what could be the suitable solution for this? So you have to choose the azimuth and elevation angles at 80 degree. Your both microstrip and dipole is providing a significant improvement at 0.5 lambda itself. So the spatial correlation is statistically reduced at 0.5 lambda itself, even though it is very minimum, sorry, this 0.75. 0.5, it is providing almost spatial correlation of 0.6. At 0.75, it is giving around 0.2 or 0.1. So we have to keep this one as 3 by 4th lambda. Then we could able to provide a significant spatial correlation to maintain the channel state information at the transmit and the receive mode. Now, for this particular model, for the same antenna, without changing the dimensions of the antenna and the basic characteristics of the array design, so you evaluate the mean capacity with respect to given SNR. You could see the capacity of this particular, the first one is the ideal model. Okay, this is IID channel. The dotted line is the microstrip channel, and this one is the dipole. So whatever may be the antenna configuration, the mean capacity is greatly increasing when you increase the SNR. This was the main advantage of the MIMO system rather than array systems or other multimode antenna systems. So this was the conclusion, stating that we can choose a proper MIMO design antennas. We can provide a significant improvement in the capacity based on the channel state informations. You can select the given SNR, and you can able to prove that these systems can be significantly proving certain applications with huge data rate. So we have continued the same work with the capacity of circular patch using multimode. Instead of arrays and MIMO, we used multimode. The channel assumptions are given here with the 20 scatterer, and the SNR is considered between these two transmitters, and the radius of the scatter disk is assumed to be 0.7. Okay, and the distance between the antennas. The first one is the IID. This one, the dotted line, is the ideal capacity. The next one is the array. This one is the array. Okay, and the triangular one is modes at the transmitter and array at the modes at the transmitter and the array. So you have single antenna operating at different modes by changing the feeding parameters or phase shift in the input signal. So this one will be the capacity of the multi-mode antenna, but both transmitter and receiver. The last one will be modes at the transmitter and the receiver. So you could see this particular model, the modes at the transmitter and receiver is reducing the encoding capacity only 2 bits per second per hertz than the arrays. So instead of using several antenna elements with a certain amount of effective cross correlation and mutual coupling, the best solution may be for the user equipments, we can choose with the multi-mode antennas, a single antenna operating at different modes, but the capacity is decreasing for the given SNR. In the meantime, the average capacity is maintained almost closer to the array and the IID. So multi-mode antenna is also a suitable solution for that. For base station, there is no problem to keep the multi-mode antennas operating either with a dielectric resonating at resonance, or you can choose metallic antennas like your horn or parabolic reflectors. But in the handset, we cannot use the metallic antennas due to the weight and the compactness of the user equipment. So care must be taken to choose these type of antennas for both transmitters and the receivers. So these are all the antenna solutions, as I already mentioned, that is waveguide based horn. The suitable one for the concept of microstrip arrays with using this waveguide approach, we call it as substrate integrated waveguide. This may be one of the suitable solution for this millimeter wave applications. Okay, so this SAW structure allows the dominant mode wave propagation through the metal cladding and the plated throughout the vias, so that the electromagnetic energy may be compared with the single antenna element. Here in this research paper, reference paper, they have considered the two substrate material with the different impedance matching ports. One is open loop, another one is slot. So this particular wave will provide a frequency ranges up to 68 gigahertz, and significant improvement in the single open loop antenna system. If you use multi open loop, you can see the current distribution at a period at 62 gigahertz at time t0, t by 2, t by 4, t by 2, and t by 4. You could see there is a huge variations in the current distribution across the waveguide. This is at the different locations with the gain, different points at the vias, so different measurement positions at 1, 2, 3, 4, like, and you can able to create a loop array, and you can create a linearly polarized complementary array with this particular design. This will be one of the best solution for millimeter wave applications. And you could see this cavity packed dipoles, the dielectric resonator antennas, DRAs, also providing a significant improvement in the impedance bandwidth and providing gain of 7.76 dBi. So these type of antennas may replace the conventional microstrip antennas. So let us come to the conclusion stating that so far I have given a light on frequencies of 5G and terahertz ranges, that is 6G frequencies, the limitations and the importance of designing this antenna subsystems with a given complexity for the given applications, and how we can able to provide huge data rate at this particular frequencies, and the role of the MIMO systems and the corresponding signal power at millimeter wave and terahertz frequencies. And we have seen the some of the critical parameters which have to be considered for successful deployment of this future wireless networks at this particular frequencies. And as I already told you, designing a miniaturized devices, since your frequencies keep on increasing, the device size becomes miniaturized, and it is very difficult to get high gain antennas. But we have to balance this gain with the compactness of the device. So how effectively your antenna design is matching with this given specification parameters to provide efficient communication system towards the specified applications. These are all some of the references. Thank you so much for your patient listening. If you have any queries, you can ask me, please. Participants, the session is open for queries.
Participants, if you have any queries, you can unmute yourself and discuss your query with the resource person now.
Hello, sir.
Yes, ma'am, please.
Thank you, sir, for nice session. Sir,
Much.
I have two questions.
Yes,
First
ma'am.
question is that since we are designing MIMO antenna in millimeter frequency range,
Yes, ma'am.
how to test the antenna because we are not having network analyzer in this
Yes.
particular range.
That's why in the beginning I
Range.
told you, if you are choosing your lower frequency ranges up to 5 gigahertz, some of
Okay.
the academic institutions like Terahertz College of Engineering, Madurai, they have their own test bench. You can test it over there. They will allow you
Yes,
to test your antenna. But if you are going with millimeter wave band antennas, now only this IIT Kanpur, IIT Kharagpur, and IIC Bangalore, in collaboration with Samir, they have their own test bed with that. So you can get permission, and you can, if you are really interested, you can collaborate with them, and you can go and test your prototype. They are allowing for academicians.
okay, okay. That's what I was asking. When
Yes,
we go for higher millimeter wave frequency range, then
yes.
very difficult to get the testing.
The
Okay.
design,
Second,
design, even fabrication, you don't get double-sided that is
yes,
PCBs to
fabrication
make your
facility
prototype.
also.
Yes, ma'am.
Yes.
You
Okay.
know, we have experiencing a very huge difficulty when choosing the dielectric substrate of these materials. So if you choose
Direct.
FR4, a
Yes.
conventional PCB, you
Yes.
cannot able to maintain a correlated values between your antenna simulation and the prototype.
Correct.
So you have to choose either electromagnetic band gap materials or photonic band gap materials, metamaterials. That may be the suitable solution, madam. Please don't try with conventional PCBs.
Correct. That's what I wanted to ask you whether we can use fabric antenna. We have heard about fabric antenna. So fabric
Yes,
antenna people are designing in the range of 2.4 gigahertz to
yes,
6 gigahertz. So my question
indeed.
was again, second question was related to this only. Can we
Okay.
design millimeter waves in using fabric antenna? I mean, substrate can be used as a fabric. So I don't think
Ma'am,
it is
it
possible,
was a
right?
big question mark. You
Yes,
usually, if
sir.
you
Yes.
increase the thickness of the fabric,
Yes.
okay, your antenna performance is not at all going to match with your given return loss and the gain.
Okay.
So
Okay.
whenever you are, and you know the fabrics are always worn in the environment like a dissipative medium. Your blood is also glowing inside the body, isn't it? So
Yes.
that particular body resistance with the dissipation will always create a strong interference, and you won't get the specified gain over there.
Correct, correct, correct. Yes, sir. Oh, thank you, sir. Thank you.
Welcome, welcome. Ma'am. I hear that KPR Institute, they have a facility, they can test up to 20 gigahertz. It's a great news. Thank you, Dr. Seetalashmi, ma'am. Thank you so much. So in India itself, in Tamil Nadu, Coimbatore, there is a college, KPR Institute, a very good college. They have a testing facility up to 20 gigahertz. You can use that also. There is another question from Mr. Vinod Rajkumar. Sir, without ANSAFT software, any simulation free version software available? Sir, at high frequencies, HFSS CST trial version is available, but you can't go beyond around some 10 or 15 gigahertz. It allows you to design antennas and simulate at 25, 28 gigahertz, but it won't allow you to optimize your own design. Okay, so better to go with the licensed version. And there is a question, sir, what type of antenna is used when optical fiber is used in base station? That is wired to wireless communication. It's the same metallic. In the transmitter base station, there is no problem. Even you can choose any metallic antennas, like your horn or parabolic reflector or dielectric resonator antenna, or you can design array of dipole. In the base station, there is no problem. Either you are using optical fiber or you want to configure with wired to wireless. You need only the isolation between the light, your optical and the RF system design. There is no problem. You can choose any type of antenna for that. Only thing is the handset, the user equipment.
Kirti Radha ma'am, if you have any queries, you can unmute yourself and discuss your query with the resource person now. Participants, if you have any queries, you can unmute yourself and discuss your query with the resource person now.
There is a suggestion they're asking, we want to enhance our 5G lab. Can you suggest? So our government is ready to fund this particular 5G. There is a collaboration. There are AICT and this IITs, they have some collaboration. You can enhance your 5G lab by creating your own test bed. This vector network analyzer itself or the testing facility itself, they are funding almost 80%. So you could able to collaborate with them. Just visit one time this Samir Center, Chennai. They have 32x32 MIMO measurement and a test bed. And the transmitter is at Samir, receiver is at IIT Chennai, ID Madras. Just have a look on it and you will get a clarity how we can able to test, like develop our own laboratory with this 5G and 6G frequencies. And we are concentrating on channel models rather than antenna design, and slowly we have been incorporating these channel models inside the system design. Ma'am, I will share my mail ID, Dr. Sheetalashmi ma'am. I will give you my mail ID. So I'll tell you later the procedure and everything. Any other queries? So slowly you can ask your BTech students in third year level and fourth year level, give them some simple projects in MATLAB and 5G toolboxes. Ask them to correlate the simple digital modulation techniques for the given channels and allow them to do some mini projects. A lot of students, they are interested. Nowadays, we could find in our university, students are very much interested to do this RF projects rather than doing with the baseband signal processing. So we can encourage our students to work with our electromagnetic things. So we need some basic knowledge about electromagnetics and vector calculus while designing the antennas and other microwave systems. That is the only problem. So we can encourage, there are a lot of scope available now. Any other questions?
Sir, shall we end up the session, sir?
Sure, sir. Sure.
Okay, sir. Thanks for sharing your valuable knowledge, sir.
Thank you so much. Thank you for the opportunity.
Thank
you,
sir.
participants, for the patient listening.
We are pleasure to have you in this evening, sir.
Have a nice day ahead. See you all. Thank you.
Thank you, sir.
Okay. I'm leaving the meeting. Okay. Have a nice day.
Okay. Thank you, sir.
Thank you.